Namaskar. Welcome to the 12th episode of Satya Samvad. What if I were to say that Pythagoras was not the one to discover the Pythagoras Theorem? What if I were to say that Blaise Pascal may not have been the first to conceptualize a Pascal triangle? The origin of both these mathematical concepts may have been much closer home, in Bharat. Bharat has had the dual of centralization and decentralization in thought. Centralization in a fundamental philosophy and way of life, and decentralization in the ways it is seen in myriad avenues of life and society. Mathematics happens to be one such area. For example, in Dharmic philosophy, the concept of infinity is significant, representing the boundless and eternal nature of the universe, as seen in the celebrated Shloka Purnamadha Purnamidam. During the Vedic period, religious texts show evidence of the utilization of large numerical values. By the era of the Yajurveda Samhita, numbers as extensive as 10 to the power 12 were incorporated into the texts. The Satapatha Brahmana, dating back to around the 7th century BCE, includes guidelines for ritualistic geometric constructions that bear resemblance to the principles outlined in the Sulba Sutra, which had one of the earliest extant verbal expressions of the Pythagorean Theorem in the world. Over the centuries, we have lost many of our traditional mathematical techniques. However, decolonization in the modern context means that we must reclaim our intellectual capital, and mathematics must be part and parcel of that exercise. To discuss all this and more, we have with us today Dr. Bhaskar Kamble ji. Dr. Bhaskar Kamble is a theoretical physicist from the Indian Institute of Technology, Kanpur, and is presently a data scientist in Germany. He has undertaken seminal research in the domain of Hindu mathematics, with a focus on important concepts such as the Fibonacci sequence, Rolle's theorem, Taylor series, and Pascal's triangle as expounded in Hindu texts. We welcome you, Bhaskar ji.
Namaste. It's really great to have you to be on your show.
So your journey from being a theoretical physicist to a data scientist to a celebrated explorer of Hindu mathematics has been a fascinating one. So can you tell us a little about the same?
Yeah, sure. I was so when I was in school, I was like I had a good education in an English medium school with a pretty good school in Delhi, and yeah, like my conception of the Hindu civilization was, from what I learned from school, it was basically that of basically a backward civilization, not even a civilization. It was more like a backward society, and with full of superstitions and like social discrimination, caste system, and all that and all these kind of pictures were also made even more acute by the media portrayals. So this was the common narrative that was around me every day when it came to the Indian civilization. And I thought, the Hindu civilization, the Hindu religion is all about caste discrimination, and I just had this notion for a long time. When I started studying physics, I was doing theoretical physics from IIT Kanpur, first from Delhi University and then from IIT Kanpur, and then of course as a physicist one has to use a lot of mathematics. So I was also very much interested in mathematics. I was, in fact, after school I was thinking if I should do physics or mathematics, but ultimately I chose physics. So I was like, so as far as mathematics is concerned, as far as the history of mathematics is concerned, I was not really thinking much about it. I thought I subscribed to the usual view that it comes from ancient Greece and it comes from later on from the Europeans. So this is what the prevalent view is, and that's what I also believed in. After my PhD, I went to Germany and to start doing my postdoc. And while I was in India, still when I was still doing my PhD, one of my friends at lunch, he told me that the so-called Pythagoras theorem is known in the Indian civilization in the Sulba Sutras. And this was sometime in 2009, 2010, and I did not take it very seriously. I thought, oh, this is just one of those hyperboles which one comes across, and so I brushed the matter aside. But after I went to Germany for my postdoc, I started becoming a little bit more interested in reading more about the Indian civilization, because I had the suspicion that that what we are being told is a lot of yeah, it's very one-sided. It cannot be so one-sided as all that. So I started reading more books on this topic, on the Indian civilization. One of the most important books for me was Rajiv Malhotra's book, Being Different. That was really a huge influence on me. And at the same time, I started becoming interested in the history of mathematics, and I was, because my whole conception of the Indian contributions to mathematics was restricted to zero. That zero is what India gave, but little more than that, nothing more than that. So I was reading a little bit more. I came across this article by John Playfair, written at the end of the 18th century, which was, given by Dharampal in his book on history of science and technology in ancient India. And there I came across the so-called Pythagoras theorem, that very mentions that the Indians made use of this in predicting eclipses much before Pythagoras. And this for me was like, I would say, the first turning point, because this showed me that what I had dismissed as hyperbole was actually true, because it comes from an independent source, which has got nothing to do with Hindu interests at hand. So I started becoming more and more interested in this. I started reading more and more journals, research journals on the history of mathematics and books. So and then I saw that it went much more beyond just zero. I mean, there was a whole like field of mathematics which was developed in India. Like absolutely, that blew my mind. And I even discovered during the course of my readings that even I came across an article by Charles Wish, which he wrote in the 19th century, 1830s, where he describes some of the Kerala mathematicians' achievements in infinite series. And I thought, oh, this so-called Taylor series, Gregory Leibniz series, these were discovered in Kerala, centuries before they were discovered in Europe. And this was for me the second, the jolt which I got. And finally, the third one, which really shook my conception, was when I read the works of C.K. Raju, where he gives the motivation, the means that the Europeans had for getting hold of this Indian knowledge, and the opportunity, and so like he describes this very, like very very clearly in his works, in his papers, and in his books. So I thought this is like really important information, because in the absence of this information, people have a very distorted view of the Indian civilization, and it's all about the caste system in the prevalent view. This cannot be acceptable. This is not acceptable. And so I started writing more about of this topic on my blogs, wrote a series of articles. And then I get kind of I thought, why not write a book on this, because it's really important. So I wrote a book, a self-published book, published it on Amazon. And I had contacts with DK Hari and DK Hema Hari from the Bharat Foundation. They put me in touch with Garuda. And then that's how I then got in touch with the founder of Garuda, Sankrant Sanu. And then we embarked on a huge editing revision of the manuscript which I had. And then after several months of editing, his suggestions, his inputs, and then my reworking of the book and everything, so it is now in the version that it is there today. So this is how the book came into being.
Wonderful, wonderful. I think that's a fascinating journey, of course, and it's so important that you mentioned one point, which is that we have this tendency to assume that it is always from the Occidental, the Western side, that we get these narratives, and to use cricketing terminology, we are always on the back foot from the get-go. I mean, even if we were to have reason enough for not being so, but that is how it is. And so it's very interesting the way the specific steps and the trigger points which led you along this journey. Now, talking of your book, The Imperishable Seed, the byline for your book is How Hindu Mathematics Changed the World and Why This History Was Erased. There have been multiple attempts over millennia to state, such as by Aryabhatta, Brahmagupta, and Bhaskaracharya, and negate various elements of mathematics that have been indigenously developed, be it in the fields of arithmetic, algebra, geometry, trigonometry, combinatorics, linguistics even, or of course, calculus as well. So how did Hindu mathematics change the world, and what was the systematic manner of negating this significance?
Yeah, I think this is a really important question. So when we speak about the aspect of how it changed the world, one can actually start seeing it right from school, in the sense that all the mathematics that we learn in school, that has its origins in Hindu mathematics, except for parts of geometry which we learn, which has clearly Greek origins. Some of the geometry that we learn, some of the geometry at least. Then like if you start as a child, when we start in school, when we start learning mathematics, we start with the concept of numbers: 1 2 3 4, 0 1 2 3 4, basically the positive numbers. Then we start getting involved with stuff like addition, subtraction, then slowly multiplication, division. Then after that you encounter the concepts of fractions, then even negative numbers, So and all these concepts were developed in the Hindu civilization, and it's like clearly like we think of them as trivial, but obviously, like it's been used unchanged since it was since it became prevalent in the West, unchanged all these centuries. So obviously, there's been something really fundamental about it, because before that, for centuries, millennia, this system was not existing in Europe or anywhere else. So it's a fallacy to think that it's very easy, or it's elementary, because and you have to also consider that it took centuries before Europe finally became comfortable with these basic, so-called basic things. Then from arithmetic numbers, one also then in school at some stage one starts learning about algebra, where you sort of this very just like numbers are everywhere in the sense of zero number system. We think of it, they are so ubiquitous that we don't even pause while thinking about how it came into being. Similarly with algebra, so when you are trying to solve an algebra problem, let the unknown be x. This is like one of the cliches of algebra. So this thing, representing an unknown by a symbol, is also a very profound idea, which developed which was developed in the Hindu civilization. We will address this a little bit later also, I think, about the how the unknowns came into being, and they were handled in the Hindu civilization, in Hindu mathematics. So in fact, arithmetic and algebra have a close relation, as we will see. And then the other topics that we learn in school, are also the subjects of like geometry. Geometry, as part of many parts of it, come from Greece, but one of the fundamental theorems of geometry, the so-called Pythagoras theorem, as you also mentioned in the introduction, that is given in the Sulba Sutras. And in fact, the impact of the Sulba Sutras is actually much greater on world history, on world mathematics, than is actually given to them. That is actually attributed to them. Then I'll talk about this in a moment. But then you also have the subject of trigonometry. Trigonometry also has its origins in the Hindu civilization, Hindu mathematics. All the things like the trigonometric circle. This is given in the Hindu mathematical texts. East-west line, north-south line. The two axes which we have. Then you have all the concepts of the quadrants, how the signs of the trigonometric functions change in the four quadrants. Even the names, sine and cosine, they come from jya and kotijya, the original Sanskrit names for these functions, and they were translated from India to the Arab lands, and from there to Europe. Similar as arithmetic and algebra, trigonometry also, and similarly astronomy also, for that matter. And when you grow a little bit older, you start learning the subject of combinatorics in school, permutations and combinations. Now all the basic formula that we learn in school today, also they were developed in the Hindu mathematical tradition by Mahavira. For example, he gave the formula for combinations. Bhaskara gave in his Lilavati, he gave all the different rules for combinations, permutations, the same rules which we learn today. And then of course, when you come to the subject of calculus, which we are taught that Newton and Leibniz, they discovered this subject, and we have this whole story of this yeah, priority between them. But actually, the basic ideas of calculus, I'm not saying, of course, the formalism in which we know it today, obviously, but the basic ideas, how to handle these infinities, infinitesimals. These ideas were all developed by the Kerala mathematicians, before centuries before they were discovered in Europe. And as we mentioned, the so-called Taylor series for sine and cosine, the Gregory series, the Leibniz series, and several other expansions for pi, they were given in the Kerala mathematical tradition. And yeah, and these are some of the things which one just does not are not known today in the common world, in the common narrative of the history of mathematics. So these are some of the aspects that one can talk about. Your second part related to how it was negated, how the history was negated, right? And I think this is a very important point also, because when one studies the history of Hindu mathematics, even in a little bit of detail, one immediately comes across the fact that the history of Hindu mathematics is also the history of how it has been, undermined, how it has been negated, how it has been, blacked out of the mainstream narratives. And it's very sad, because even many Indian faculties of in renowned research institutes of mathematics and so on, even they sort of don't kind of agree. They deny it, that this sort of a negation has taken place. I mean, I had some interactions with some of these professors, and it was a little bit disappointing for me to see that this is the case. But if you look at the history of Hindu mathematics, and also the perception of how this was received by the Western scholars, you can identify certain trends how this was done. So there is a very systematic. You can kind of list out a certain number of ways by which this is done. So, for example, one of the most common methods was to date the Indian text to much later, so that you can impute a Greek influence on them or a European influence on them. This can be seen, for example, in the case of the Sulba Sutras. So they became known for the first time in 1875 in Europe by the translation of George Thibaut. He translated them into English, and then the Western world was confronted with the possibility that Greece may not have been the originator of geometry. It could have been the Sulba Sutras. And then suddenly there was this very well-known German historian of mathematics called Moritz Cantor, and also the many others. They started saying that Sulba Sutras were written in 150 CE, so to speak. So that then it becomes very easy to conclude for them to conclude that they were influenced by Greek geometry. So this is, and then this is also the same situation we see by other people like James Mill. He also wrote the same thing in his book on the history of British India. Then the same technique also you see, for example, in a recent case by not recent but comparatively recent, when we in the history of mathematics, when we take the case of Augustus de Morgan, he claimed that the series expansions of sine, cosine, etc., that were known in India, they were actually the Indians came to know of them from certain European scholars, and then they passed it off as their own. So this was Augustus de Morgan, and this Professor M.D. Srinivas, he has documented this in his article on Bhavna, very nice article on the historiography of calculus in India. So this is one of the things. Then one of the ways by which it is minimized. There are other ways. So the other way is that you downplay its significance. You somehow claim that it's not so significant. So this you can see in the case of zero. So zero is probably like Western historians have claimed, have read their books, that it was just discovery waiting to happen, and it was just by luck that the Indians discovered it. So and also the similar idea you see in the subjects in the field, in the topic of irrational numbers, rational numbers, negative numbers. The Indians developed the concept of negative numbers. Yeah, Brahmagupta, for example. But then if you look at the writings of the Western scholars, they would impute this to just sort of the lack of rigorous thinking on the Indians, which made them make such what do you say? This was basically these are like underhanded compliments, right? So, but it needed the rigor of the West, which put the real number system on a firm theoretical basis, rigorous footing. So these kind of techniques are used for negating. I would also like also mention here this, one of the other ways of doing this is this magnifying the Greek mathematics narrative, that everything comes from Greek mathematics, as we saw. And then we also have things uh, like the Babylon, if not Greek mathematics, these days it is this Babylonian mathematics. So so again like Sulba Sutras, Pythagoras Theorem. These days when you do any like internet search on this, you will most definitely hear Babylonia, but not the Sulba Sutras. So this is also another way of. And in fact, for Babylonia, there is also a reason, because Babylonia was one of the cities mentioned in the Bible, and many of the cities in the Mesopotamian region, they are mentioned in the Bible. So this becomes also like important for the Western civilization to locate this in their own trajectory, so to speak. So okay, so I think yeah.
Absolutely. So many nuances to it, right? I mean, so many aspects, as you very beautifully elucidated. This is the aspect of trivialization, of course, of one side, and the magnification, the amplification of the other. There is, of course, the displacement of the reference points, right, so to say, which we had a discussion on in a different context a few episodes back on that as well. Now, my question to you is actually would be twofold based on what you just mentioned, which is that one is the experts themselves, the scholars of Indian mathematics, Hindu mathematics as such. We know that many a times within poetry, within language, I mean, there's an encoding of many mathematical concepts, for instance, and there could be ways in which especially over narratives that have been spoken rather than written, and in encoded form rather than in explicitly kind of visible form as such. There could be many things in mathematics that have been around for a while, right? So firstly, the discerning or the decoding of that is, I'm sure, I mean, you would, of course, know more about this, is quite a monumental challenge in itself. and to kind of pin it down to where it went back to, right, in terms of historicity or in terms of the chronological aspect of it, is a very important aspect that has to be looked at closely. The other thing, the other side, of course, is when the common public is the masses are confronted with this narrative, either from the West or from various other cross sections, that this is where it came from, and what you're saying is quite trivial. It's not quite as important. How do you see us as a nation, as a civilization, working towards making things more accessible, making this narrative more widespread within the masses as such, so that we can counter this?
I mean, I think that for sure, people, I basically, this is also the question which confronted me in the first place. And my solution to this was, okay, that I should, in my capacity, I should, make this information accessible to more people by maybe writing this book or writing blog posts, or that in my personal capacity, I saw that as the solution. But I think it is also something which has to be done on the level of the state, because an individual can do only so much. An individual has limited capacities. So this is where I see that where the state really has to come into the picture and take a step up the game. But unfortunately, without going into political aspects, I think I see that is not to be happening. Actually, I see that is like something which is sorely missing. Yeah, but I think at the same time, in the absence of that scenario, I think we as individuals have to take the initiative also. Like parents can teach their children, can make their children more aware about this, and yeah, I mean, on an individual basis, I think I cannot say more about this as right now.
As for the encoded bit
Yeah.
of the knowledge itself, and how you yourself went down this path of course, Sulba Sutras have been written upon previously as well, and there are a few other works on the Satapatha Brahmana as well, if I'm not mistaken. But in the context of other works which are still out there, and there is a whole lot of them, so to say, there is obviously this intersection of linguistics and mathematics, and a few other aspects as well. So it's a fairly non-trivial challenge, so to say, right, to kind of pin down the conceptual constructs and the elements which are out there. So
I would also here maybe point out that decoding this things, this information is actually can be quite non-trivial. So when we look at the work of Pingala's Chanda Sutra, for example, he gave his sutras in a very short, very terse kind of ways, just a few words each sutra, and we are dependent on the commentaries of later day scholars like Halayudha, who who have that actually the information decoded that, and there are so they were meant for memorizing and passing down from generation to generation, and they also had the rules for decoding this. And in fact, there are some interesting papers by Subhash Kak and I think Amba Saraswati, I think one of his co-authors. They have in fact discussed this. So yeah, this is actually a deep topic, and unfortunately, I have not delved into it with any detail. But that would take that would be quite an interesting excursion.
Right, absolutely. Now, you have also written about ontological concepts going beyond and besides mathematics, and that relates back to what we were just discussing, of course. When we speak of the reality of the universe, we have various fundamental questions on the ontology as well as epistemology of various systems. In simpler words, we must discuss the reality of nature at its root, as well as what knowledge of nature implies. So from the perspective of Hindu mathematics and Indian knowledge systems, as per your explorations, relating to the physical sciences especially, how do you conceptualize and interpret nature and knowledge within the Bharatiya Gyan Pranali context?
Yeah, this is also one of the aims of my book has been to also show this Indian mathematics in the context of the Indian knowledge system. And because many of the books I saw that deal with Indian mathematics, they treat of mathematics as an independent phenomenon, independent of the background from which this knowledge arose. So in fact, this I wanted to also bring this aspect of the philosophical background in how this mathematical knowledge is located there. But for that, we need to also understand how how knowledge itself and the universe itself is conceived of in the Indian system. So in the Indian system of knowledge, or in the Indian worldview, so to speak, the whole universe is divided into two parts, two aspects. One is the so-called this observed, the part which is observed, which you can observe, and the other part is the observer. So these are the two fundamental aspects of nature, of the universe in the Indian system. And it's the observed part is, so to speak, the apara prakriti, and which is constantly changing. So it consists of matter, and like not just matter, not just a material universe, but also things which relate to the mind. So the mind, emotions, feelings, and ego even. So this belongs to the so-called apara prakriti. And the other part, which is the observer, is the one which is not changing. It does not have a beginning and end. And this is the so-called para prakriti. And this is like, the eternal or the undying reality, which is the witness to everything. So, and this is also given by different names in the Indian system. So for example, it's also known as kshara and akshara, that is the perishable and the imperishable. It is also known as kshetra and kshetragya, the field and the knower of the field. And also like vyakta and the avyakta, that is the manifest and the unmanifest. So known and the unknown, these kind of divisions are made. So it's really interesting that that the this nature, this knowledge of this nature is also divided into two parts, correspondingly, the so-called paravidya and the aparavidya. So aparavidya is all the knowledge which deals with the the changing universe, the apara prakriti, right? So mathematics would definitely be a part of that. All the physics that we learn today, and the sciences, and even all the other systems like political systems, political knowledge, philosophy, etc., at least pertaining to the apara prakriti, that would come under the foray of apara vidya. And then the other part, for when you when you want to know about the para prakriti, that's when you about the atman, paramatman, and the bhagavad tattva, then you have the field of para vidya. And it's obvious that the techniques which you use for obtaining apara vidya cannot be used for obtaining para vidya, because the means of achieving knowledge in the apara realm of apara, that is to say your senses, your mind, intellect, they are themselves part of the apara prakriti. So they cannot be used to access the para vidya. So for that you have yogic techniques and all that. So which is the so-called para vidya. And yeah. So, and interestingly enough, the two of them are not separate from each other. The paravidya and the aparavidya, they complement each other, and at the same time they actually basically they complement each other. So for example, if you like so for example, if you want to attain paravidya or moksha or things like that, so but you cannot do it without by simply separating yourself from the world. So you have to be in this world. Like even Arjuna was told to fight the war, even though he said that I want to go and live the life of an ascetic. But he said, no, you have to fight this war. So you have to be in this world. So in that context, it becomes also important to attain a knowledge of the apara prakriti, and that's where apara vidya comes into play. So these are some of the aspects, and I say, and therefore different fields like astronomy, like agriculture, and yeah, navigation. So for all these things, they come in the purview of apara prakriti. And also mathematics was developed in the context of many of these applications like astronomy and navigation. And interestingly enough, the concept of paravidya and aparavidya has also interesting influence on the development of mathematics. So so this distinction into para and apara vidya is only at an initial level of understanding, when when one has not really attained the state of enlightenment or experienced that supreme reality. But at a deeper level of understanding, one sees that these two are not actually separate. They are actually there is actually only one reality, and it makes no sense of talking about para and the apara, because it's like because the real and the unreal, so to speak, they don't have an independent existence. It's like they need each other for their own definition, so to speak, right? And so this whole concept of this para and apara is also more subtle than just this division. They become one, so to speak, at a later level, the so-called integral unity, where also this is, the same paramatman is the same as the jivatma, when one reaches that state of enlightenment. So the way this so this has had also interesting influence on the development of Hindu mathematics. So for example, if you look at the concept of zero, so zero is like a number which is like which like does not exist, so to speak. So similarly, in the Bhagavad Gita, you have statements like Sadasa Chaham Arjuna, I am being as well as non-being. Arjuna says. Then there is also in Krishna says, sorry. Then in chapter 13 there is this phrase. Uh, uh, na sat and it is satta nasad uchyate. Yeah, sat tat na asat uchyate. So it is said to be neither truth nor untruth, neither being nor unbeing. So from here you can see some clues. Maybe like this is speculative, of course, but how the concept of nothingness could be like given a form in Hindu mathematics, and also the concept of algebra, not sorry, algebra, infinity, which was given, which was expressed by Bhaskara in his work on Bija Ganita, where he compares this infinity, to Lord Vishnu. No matter how many beings arise of Lord Vishnu or how many beings go back into it, there is no change in the supreme reality. Likewise, in this Kahara figure, no matter what you add to it or what you remove from it, there is no change in this, which of course is also reflected in this verse that you quoted at the beginning, Purnamadaha Purnamidam Purnat Purnam Dachyate. So these are some of the things I think which come to my mind when I speak about.
And I think it's very pertinent to highlight what you mentioned about contextualization, because sometimes there is this bid to uproot a certain knowledge system from the broader context, so to say, from the point of origin, in a manner of speaking. And you mentioned about this method of knowledge generation and how it is kind of proposed in terms of a framework. Within the Hindu philosophy, of course, we have the darshan, we have the ideas of praman as well, and the manner in which reality is oriented in different levels of existence. So as you rightly mentioned, there are aspects of dualism, for instance. There is also monism, if you will, in the modern parlance. So all of them kind of have different domains or subdomains, or could possibly inform mathematics as well, I'm sure, in your exploration, as you mentioned. And we should be very kind of mindful of the fact that it should not be decontextualized, so to say. Now, you mentioned in one of your responses about the quote-unquote exploits of the Greeks and the Romans, right? And there has been a lot written on the exploits of these civilizations in the areas of astronomy, for instance. And however, there is an interesting point, which is that there may have been an inadequacy of their numeral systems to represent different kinds of numerical values required for some of these pursuits. So there is a certain kind of inconsistency or a contradiction of sorts, where there isn't a tool, but there is the news, or there is this coverage of the exploits, so to say. You have also highlighted that the likes of Al-Khwarizmi and Fibonacci may have been familiar with Indian mathematical traditions and achievements. You have rejected the premise that Al-Khwarizmi or Diophantus, for instance, were the ones who established algebra, going on to highlight that the Bharatiya works on algebraic operations have been seminal in themselves. So how does this contextualize Bharat's ancient and medieval mathematical attainments in the international system of knowledge over the ages?
Yeah, that's actually a good point with regarding the Greeks. So in fact, I have also quoted some Western historians where they say that it's remarkable that Archimedes achieved what he did with his knowledge of fractions in like it, right, and this also we see in the astronomical works of, for example, Ptolemy. So for astronomy you need really a good way to calculate numbers, a lot of computations you have to do, right? And then we suddenly see there is so much of this mathematics is ascribed to them, whereas this becomes a little bit inconsistent with the fact that they did not have a way of doing arithmetic or numerical computations. So actually the thing is, with the Greek narrative, it's in fact, if you look at the history a little bit more closely, the thing is, most of the Greek mathematics that are ascribed to the Greeks, they come from really later dates, like really later, like 7th century, 8th century CE. Whereas Euclid is supposed to have lived, I don't remember, maybe 300 BCE. So there's like a difference of between 500 years and 1000 years, between the time when the supposed creators of this knowledge were lived and their first appearances, the first manuscripts from which they were translated back into Latin and Greek. So this thing is and I have discussed about this in depth in my book, with how this was done and the whole thing. So it becomes really questionable to ascribe all this mathematics to the works of Euclid, Archimedes, and the Greeks, because you never know how much is their original work and how much is the work by subsequent by subsequent scholars, right? And so this was in fact, a ploy used by the church to impute the so-called, the pagan philosophers of their time, the knowledge of their of these pagan philosophers to early, figures, so that they could not face any threat from them. At the same time, they could blot out these contemporary philosophers. And obviously there has been a lot of, additions by later Arabs, and also in these texts. So this whole thing of Greek mathematics is something that has to be seen with much more care. Now, as regards the works of Al-Khwarizmi and Diophantus, there is obviously, there is, in fact, there is no doubt. I mean, it's just a, like, very established sort of falsehood in the narrative of mathematics, that Al-Khwarizmi is the originator of algebra. I mean, everywhere you see on the internet, on all the people, they just keep repeating these things, but it is absolutely untrue. The concepts of algebra, representing an unknown with a symbol, that comes from the Hindu civilization, and that started with Aryabhatta and was, Brahmagupta, and Al-Khwarizmi was well acquainted with the works of Aryabhatta, Brahmagupta, and Bhaskara, and the, other subsequent, and the other mathematicians, in this time, because and because, like, once India fell, once the province of Sindh was conquered by Muhammad bin Qasim, the Arabs got access to the Indian texts of mathematical texts, and, Indian envoys would be sent to Baghdad, and there, this mathematical astronomical text would go there, and these were then used by Al-Khwarizmi, and he just, he kind of, used this knowledge, and wrote his two books, one on arithmetic and one on algebra. And this is how somehow the whole myth began, that algebra and arithmetic, they come from the Arab knowledge, Arab system. In fact, even the word Arabic numbers is such a misnomer, whereas it's Al-Khwarizmi himself claims, he himself states that these are Indian numbers. Fibonacci also himself states that these are Indian numbers. So it's absolutely yeah, unacceptable that, the Indian contributions of algebra are totally ignored, and it's all attributed to Al-Khwarizmi or Diophantus, for that matter.
Right. Absolutely.
Yeah.
I think the chronology is so conspicuously, coincidental, or, just tailored in the manner where this, or the points that you just mentioned are fairly obvious if you think about it in a greater detail. You mentioned this point on, the variables, or how we used to express, the unknowns, so to say. And in a previous response, you mentioned about Bija Ganita, which is root mathematics. Within Bharatiya traditions, we have also had Avyakta Ganita, which is the mathematics of the unexpressed. This is particularly interesting since many of the Hindu shlok that express the numbers and mathematics are by definition and characterization poetic. And which I just mentioned in one of our previous, dialogues on one of the points, they have this encoded structure to them, thereby leaving space for the dynamics of the knowns and the unknowns. You have yourself highlighted how mathematical variable definition was known, and the concept of the unknown quantity was referred to as Yavatavat in Hindu mathematics, with applications even in quadratic equations. The concept of the unknown, the uncertain, has been of great importance in metaphysics and philosophy in general the world over. So can you tell us a little about how our Bharatiya civilization handled this central element within the mathematical fold?
Yeah. So in the Indian philosophical system, you have the concepts of, the Vyakta and the Avyakta, and interestingly enough, arithmetic in Indian mathematics is known as Vyakta Ganita, and algebra is known as Avyakta Ganita. And in fact, yeah, so in the Indian of so in the mathematical system, as so Vyakta refers to something that is concrete, that is something which has a name and a form, nama rupa, right? So name and a form, so something concrete, physical form, or something, which you can see or is there. So that way you can it's easy to understand why arithmetic is known as Vyakta Ganita, because it deals with specific numbers, which have a quantity and things like that. So, and whereas Avyakta Ganita deals with unknowns, so which are denoted by symbols. So so I just yeah. So right. So in fact, how to say this? Yeah. So 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 there's a close connection between how the concept of arithmetic gave rise to the concept of algebra. In fact, it's not, when you look at it in hindsight, it's no surprise that the same civilization which gave rise to arithmetic also gave rise to the concept of algebra, to the concept of avyakta ganita. So to understand the connection with the Hindu philosophical thought, avyakta is something that is unmanifest, that you cannot see, that is there, and it's also known as it's also called as the unknown. Avyakta is also called as the unknown, and it's like the root, the seed of the entire universe. So the vyakta has its or source origin in the avyakta, in the unmanifest. So for example, one of the verses from the Bhagavad Gita, it says avyaktad vyaktayah sarvaha prabhavanti haragame. So out of the avyakta comes the vyakta. So in fact, um, so how do I say this? I think I'm just trying to think of how to. Yeah. So from the avyakta comes the entire vyakta universe. So in the same way, like when you think of the specific results of algebra, specific statements of algebra. So for example, you just take a right angle triangle where you have the sides A, B, and C. So you have this relation that A square plus B square is equal to C square. So this is like the avyakta from which you can create any right angle triangle. So this one expression contains all the right angle triangles that can ever exist in the plane. So that way you can understand how the algebra is like the source of the specific cases of arithmetic, right? And in fact, and this also in this sense, one can also understand that the avyakta is like the seed from which the entire creation sprouts. So that's why it's also known as bija. So the avyakta is also known as the bija, so seed. So one of the verses in the Bhagavad Gita says that bijam avyayam gatir bharta prabhu sakshi nivasah sharanam suhrit prabhavah pralayah sthanam nidhanam bijam avyayam. So avyayam bijam means basically imperishable seed. So that's how the source of the title of my book. And this idea was explicitly also mentioned by mathematicians such as Bhaskara too and Narayana in their works. So I have this one verse by Bhaskara too from his text Bija Ganita. So he says, Utpadakam yat pravadanti buddhehe adhishtitam satpurushena sankhyaha vyaktasya krishnasya tadeka bijam avyaktam isham ganitam cha vande. So it basically means that I revere that avyakta. So this verse by Bhaskara has a double meaning. So on the one hand, he refers to the avyakta and the vyakta as understood in Hindu philosophy, and at the same time he refers to vyakta and the avyakta mathematics. So I revere that avyakta, that is the supreme being or the supreme reality, which seers or rishis declare as the originator of clear intellect and the sole cause of the vyakta, that is the universe. But at the same time, it has a double meaning that I revere that avyakta ganita, that algebra, so to speak, which instead of rishis, you can also have the word mathematician, because he uses the word. Um, okay, I'm not able to find that word right now, but yeah, he uses the word. The word for rishis can also be a mathematician. So the mathematicians declare this avyakta as the originator of the vyakta ganita. So, and there's also very interesting way in which the mathematical equations were formulated in the Hindu texts. So if you want to write so one of the words they used was, which we call today as X or any unknown, they used the word yavat tavat, and they shortened that to ya. So ya would be the sort of, the version of today's X. So if you want to write, for example, 5x plus 1, so they would write 5, the number 5, then they would write the letter ya, and then instead of plus 1, they would write ru, and ru would be the short form for rupa, and then they would write 1. So rupa means form, so which refers that we are dealing with a form of 1, so it's like plus 1, the specific number 1. And then the other side of the equation, whatever it is, they would write it below that. So instead of right and left, they would write up and down. And in fact, as I had mentioned, the arithmetic and algebra have a very close connection. So if you look at arithmetic, how numbers are added, numbers are 531. That's actually a power series in 10, so to speak. Not a series, but just an expansion. 5 times 10 squared plus 3 times 10 plus 1 times 10 to the power 0. So in the same way, you can also add different terms, different powers of, for example, X. And this is exactly what Brahmagupta also said. Like when we add different terms involving different powers, we add them in the like terms together, and basically, like, just the way we add up numbers. So there is a very close connection between arithmetic and algebra, and how algebra is the generalization of arithmetic. For example, this has also been discussed by the Hindu mathematicians like Bhaskara and Brahmagupta and others. And interestingly enough, even Newton, called this algebra as the universal mathematics, and he makes this same generalizations between arithmetic and algebra. And as I have quoted also in my book at one of the places. So yeah, so this is what I.
Very interesting. And I think the whole idea of the avyakta and vyakta, also in the context of, uncertainties as well, because, that has been an area of interest for myself, which is that of how do you deal with uncertainties, for instance, in the physical sciences, within the application of mathematics in different contexts as well. And the margin, so to say, when you're talking about numerics especially, is of importance in many different contexts. Now, coming to a very, very important aspect on which deals with arithmetics and algebra, and for that matter, computation also in the modern parlance, is algorithms, of course, right? And algorithms are the building blocks of functional as well as object-oriented, if you will, infodynamics and mathematics. Bharatiya traditions have had various kinds of algorithms, such as the Kutaka and the Chakraval algorithms. This went hand in hand with the development of various tools of representation theory, which is basically how you represent the different kinds of mathematical entities, for talking about the zero, for discussing negative and fractional numbers, and even to denote large numbers. So how did this algorithmic approach play a pivotal role in the evolution of Hindu mathematics?
So in fact, it's totally it's a very interesting point that algorithms have played an important role in Hindu mathematics. So we see that right from the when we consider the mathematics of that we use in arithmetic, the arithmetic operations, addition, subtraction, multiplication, division, which we learn at school, right? So they are also just basically we do them. School children learn these rules blindly because they don't need to understand them. But these are actually, so to speak, algorithms. Even algorithm is a word which comes from al-Khwarizmi, but yeah, so is it, so it is. Yeah, so but these so-called algorithms were developed by the Hindu mathematicians, of course, in the course of their work, and this is what we use. Children are taught, and they learn in school. So apart from that, there are also the subject of linguistics and prosody. This is also, and even music. This is also a rich source of algorithms. So in the field of like prosody, for example, where you have the different chandas, the different poetic meters. The Hindu prosodists were very much interested in certain key questions. So, for example, given a certain type of poetic meter, how many meters can I make of how many meters exist of this particular type? And then how can I index these meters? How can I arrange them in a certain order, in a certain sequence? And once I have arranged them in a certain sequence, how can I, given the index, extract the meter from there, and vice versa? Given the meter, get to know what the index is. So these, and then so this is, for example, you see in the works of Pingala. So where he speaks about the so-called Varna Vritta meters, poetic meters with the same number of syllables. There he gives there he develops the idea of the Meruprastara, the so-called Pascal's triangle, and in that context he also he he sort of lists out basically the different meters that are possible, and in the process he develops this so-called he develops this the first ever known instance of the binary system, which lets you go from normal numbers, decimal numbers, if you will, to the binary representation, and vice versa. So because this deals with basically meters which represent which have contained two types of syllables, long or short. So if you look at the details of this, the L, the long and short, they become two symbols, and they can be used for representing these numbers. So he also was interested in this this algorithms called Uddishtam algorithm, and the algorithm for the Nashtam. So for example, when you have a index, so suppose a poetic meter got lost, but you have the index, the index of that. So how to go from here to the meter and vice versa. So actually this is closely related to the whole idea of binary numbers, which we just saw. then you have the same ideas of enumerating different meters and chandam and the uddishtam and the nashtam in the case of the so-called matra vritta meters, where instead of the meters having equal number of syllables, they have equal time units. So equal time units. So basically, this is where you get the so-called Fibonacci sequence, before Fibonacci. So this was given by Halayudha, Virahanka, not Halayudha, but Virahanka and Hemachandra before much before Fibonacci. I think in the 8th, 9th, 10th centuries in this time scale. So there you also have algorithms for going from for basically again going from the index to the meter and vice versa. And I mean, in music, of course, Sangita Ratnakara, I think there's this text where also a lot of things related with combinatorics, permutations and combinations are discussed. And in fact, even the subject of permutations and combinations in Indian mathematics, they are closely related to this algorithmic approach. And as you mentioned, the very important algorithms of Kuttaka and Chakravala, they were also really huge steps that were done by the Hindu mathematicians. So the Kuttaka algorithm, for example, you have the so-called linear Diophantine equation ax plus by is equal to 1. So where all are integers and you need integer solutions in x and y. And you have the so-called the Chakravala algorithm, which was so the Kuttaka algorithm was given by Aryabhatta in the 5th century, and the Chakravala algorithm had a history, like with Brahmagupta and Bhaskara, Jayadeva, several mathematicians, and it was finally solved by Jayadeva and Bhaskara in the 12th century with it deals with the so-called second order Diophantine equation. So equations of the type nx square plus 1 is equal to nx square plus I forget, nx square plus 1 is equal to y square. Yeah, nx square plus 1 is equal to y square. So these sort of equations were used in astronomy. So for example, the Kuttaka algorithm, when you have two certain events which occur periodically, you have to, when does it occur at the next time, so to speak, that sort of a thing. And this so-called Chakravala algorithm was used for example, finding approximations to square roots of numbers, and things like that. So in fact, the Chakravala algorithm also has a very interesting history in the context of European mathematics. So this equation nx square plus 1 equal to y square, this was proposed by Fermat of the Fermat's last theorem fame, and he proposed it to he gave this challenge to other European mathematicians. This was, I think, in the 17th century, and he challenged them to solve it for the case of n equal to 63, which has really a huge representation for x and y, huge numbers for x and y. And interestingly, this very equation for n equal to 63 was solved already by Bhaskara and Jayadeva in their works in the 12th century. So yeah, and in fact, these algorithms also, they contain many key ideas, such as principle of descent. So that where a series of numbers, you go from one step to the other step, so you have positive numbers, and at the next step you get a smaller number. So, and it's always positive, so at some point it terminates, so in the end you are assured of a solution. So kind of things. Yeah.
I thought you mentioned about Pingala and about the I think it's the binary table generation. There is an algorithm, I think, where he talks about a very systematic manner of looking at the tabulation of sorts, I mean, which people have worked on in terms of tabulation of those numbers. I'm just curious, you mentioned about algorithms, the term itself. Do we have a term that you came across for algorithms within your studies from our Gyan Pranali?
I, to be honest, I don't remember actually. It could be that I was not careful enough, but I did not really come across a specific term.
Right.
Yeah.
Because I think that would be an interesting kind of,
absolutely, yeah.
If you can have something along those lines. You have also worked on geometry, and we have spoken about this as well. And within Bharat, the applicability of geometry in social life and rituals, right? We have spoken about the Sulba Sutra. It has been seen in that with the designing of Vedic altars. You have spoken of the origin of the sinusoidal functions and, against the Western claim of the Pythagoras theorem already, besides highlighting how the value of pi had been given by Aryabhatta. So can you tell us a little more about how Bharat has been a pioneer in geometry and trigonometry in a very contextual and a very kind of society-oriented manner as well?
So the subject of geometry, trigonometry especially, is very important in the subject of astronomy. So in fact, most of the Indian Hindu mathematicians were astronomers, and they developed this mathematics as a, like, to develop the astronomical knowledge. So, and astronomy in turn was related very closely to the calendar. So the Indian calendar, Panchang, or the different calendars that are used. So they were closely related to this. And at the same time, navigation is something that uses astronomy a lot, celestial navigation. So Indians, they conducted trade with several countries in Africa and also in Southeast Asia. This is like, yeah, this is well known. In fact, when Vasco da Gama, he came to India from Africa, he actually took the help of an Indian to sail from Africa till the coast of Kerala. This is written in one of the, log books of one of his people who traveled on his ship. So this is there. And then of course, like, these are really practical applications, like navigation and astronomy. Then of course, in town planning also, architecture, town planning, you need to have a knowledge of geometry for sure. I mean, in fact, the Sulba Sutras, they contain rules for even finding the directions of the east, west, north, south. In fact, this is so-called circle method for finding the directions east, west, and north and south in the Katyayana Sulba Sutra. So it's really interesting that, yeah, this is a very simple process, a very simple method, which kind of, neglects the fact that the Earth is revolving around the sun. So these subsequent corrections to this term were given by later day mathematicians like Shripati and I forget, in I think the 12th century. So it's also really very sophisticated bit of trigonometry to carry out this correction, because you need to know how the sun is moving on the celestial sphere and things like that. Yeah, I think town planning, architecture, temple building, I think these are some of the things that come to my mind when I speak about the applications of geometry and trigonometry.
Absolutely.
Right.
I think, we recently, have seen the Sri Ram Janmabhoomi Tirth kind of Pran Pratishthan, and there we have the Tilak, the Surya Tilak, so to say. But there are temples from the past where we see the alignment of the sun, for instance, on the deity and in various parts and segments of the temple, oriented around different parts of the year, so to say. And that also obviously has a lot of calculations with regards to astronomy and mathematics, of course, geometry in particular. You have been speaking about permutations and combinations, and that is of interest to me because it also relates to one of the fundamental strands of philosophy in Hindu Dharma, which is Sankhya Darshan, which also talks of everything we see in the world and in the universe as permutations of the gunas, right? The fundamental qualities of nature. You in your work have written about Mahavir's formula for the basic combinatorial expression NCR, as well as Bhaskar's extension to the conceptualization of the basic permutational element NPR as well. Can you tell us a little about how our philosophy and worldview may be based on an advanced understanding of permutations and combinations as put forward in the Bharatiya Gyan Pranali?
Actually, when we think of permutations and combinations, it struck me at some point that that they are also closely related to the concept of fractals or self-similarity, because when you look at some of the earliest examples of combinations that occur in Hindu mathematics, that is the so-called Meruprastara by Pingala, the so-called Pascal's triangle. So where it basically, it lists out all the different numbers in this triangle are actually of the form NCR. So 1 1 1 1 2 1, etc. Right. And it's very interestingly, each term in this is like, the sum of the two terms above that, right? And this comes from the recursion relation for permutations and combinations, where NCR is equal to n minus 1 CR minus 1 plus n minus 1 CR. So it's like, this this kind of a thing is there, so where and each term in turn, like n minus 1 CR minus 1 and n minus 1 CR in turn is given by two other terms preceding that. So it's like, there is a self-similarity itself in the nature of these coefficients, in the nature of these terms. So and this is something that that also runs in several of this other kind of let me have a look at several other themes of Hindu philosophy. So, for example, like you have this concept of Vara Sankalita by Narayana Pandita, where you have the sum of sums. So each you have a sum of the first few numbers, 1, 2, 1 plus 2 plus 3. Then you take the sum of the first partial sums, and you keep on repeating this process again and again. So again, like this sounds like it's a very complicated thing, but surprisingly enough, the answer can be found very easily with the Meruprastara itself. So in a few lines. So it's like again this concept of like self similarity is there. Then if you look at the self similarity when it comes to this the definition of the Vara Sankalita, then you look when you look at the different the so-called prastaras, like not just the Meru Prastara, but the expansion of the tables, for example, the Varna Vritta meters and the Matra Vritta meters. So when you look at the how the different meters for the Varna Vritta are enumerated, there also you see a certain self similarity. So you have, for example, like with just one matra you have laghu, so L. Then you have just that, and then you have another, like suppose two varnas are there. You can have either LL or actually I kind of think, or you can have LG, GL, and GG. So it's like you kind of build it on the basis of the meters which were having only one varna, and so that's how you get this expansion. And there also you have this theorem of this, not theorem, but this principle of self similarity. I don't know if I've been able to express this properly, but
Yes.
okay.
I think self-similarity itself,
Yeah.
we talk
Yeah.
about many aspects of Vedanta as well, and many other
Yeah.
darshan. We talk about the decentralization of the universal, right? Obviously Atman, and when we talk about Atman and Brahman, we're talking about more spiritual dimensions, of course.
Exactly.
But everything is repeated across the scales, right? I mean, that is a beautiful thought, and I think there is a position, there's a statement, or there is a conjecture that the way the ancient seers used to have insight into many mysteries of the universe was because everything is decentralized in us as well, or in more accessible terms to us, using the principle of self-similarity.
Yes, there is
So
this famous statement, right? Yatha pinde tatha brahmande.
Yes,
That's what.
absolutely. So, when people say we didn't have the labs and, we didn't have many other aspects, well, it's still out there that we can't make a conclusive statement, so to say. But
So,
I mean, the hypothesis is that self-similarity may have played a
I
role.
just wanted to like just make a point, because you raised the point of permutations and combinations. I just wanted to say that that these were closely related to the subject of prosody, to the poetic meters, and these were in turn closely related to the concept of self similarity, so to speak. And this is so Pingala's Prastara was based on this recursion relation, and you have the same sort of self similarity also in the Matra Vritta meters. So Sn is equal to Sn minus 1 plus Sn minus 2, the so-called Fibonacci sequence. And also, I mean, and of course, this is what I would just say on this topic. Yeah,
absolutely. And you mentioned about prosody, you mentioned about poetry right now. The next natural question, of course, is regarding language, right? Language is based on this concept of articulation, right? I mean, language is not just language as we use it, but even mathematics, for that matter, is very much a language which we have used for instance, the physical sciences, for physics, to explain how nature works. So linguistics is the science of employing, these phonetic elements in semantically meaningful ways. You talk of how Acharya Panini's work is very important, since only 4,000 rules approximately are sufficient for generating various phrases and sentences within Sanskrit. The fascinating side to this relates to the iterative and recursive methods that are employed, similar to how modern day computer science works, laterally referring to the conceptualization of what can be regarded as the binary numbers themselves. There is seemingly also a connection between the Varna meters and the Matra meters in Pingal's Chanda Sutra with the binomial theorem, as well as other mathematical operations. So can you tell us a little about this?
Yeah. So like yeah. I mean, the thing is with linguistics is that it is so one of the biggest linguist, most famous linguist was Panini, who wrote this Ashtadhyayi, and this was about in the 500 BCE or so. This at least this is what is given the date of Panini and Pingala also. So there, as you mentioned, he gave a set of rules about 4,000 in number. So the beauty of this was that you can not just break a sentence into its constituent parts, but also you can do the reverse. That is, how can you use the constituent parts to build meaningful sentences? So his ideas in the subject of linguistics have been extremely influential in the modern world, in the subject of linguistics itself, of natural languages, and also programming languages. So the subject of linguistics, in fact, in Europe took off only after the works of Panini became available in Europe. And most of the linguistics, many of the well-known linguists of Europe, for example, Leonard Bloomfield from early part of the 20th century, I think his works have been shown to be influenced by Panini's works. And even later Noam Chomsky, in the second half of the 20th century, his works have also been shown to be uh, some of his works have been shown to be related to Panini's works. And in fact, in computer programming languages, you have this so-called Bacchus Nor form. So it's like this was given by Panini in his Ashtadhyayi for the first time, and this was like used for computer science, computer programming languages representation for them. So I mean, apart from that, I think I'm not so much it's a vast field, linguistics, and I think I have not gone into it in so much more detail. But
And
yeah,
absolutely. I mean, there's this
yeah,
intersection between linguistics and what you just mentioned about in terms of representation of mathematics and the usage within information theory as well. I mean, there is
yeah,
the discussion on programming and how Sanskrit, for that matter,
yeah.
is a very powerful can be a tool for representation theory within the infodynamics domain as well. So that is a very important point that you have deliberated on and you mentioned to us about. Now, a discussion on Hindu mathematics is incomplete without talking of the Kerala school of mathematics. We all know the sign tables of Madhav as well as the works on the Leibniz and Gregory series. Can you tell us a little about the significance of this school of mathematics?
Yeah, I think the first point that must be mentioned in this context is that the Kerala mathematics again was not a independent phenomenon. Like it has a long history and continuous history, starting all the way going all the way back to Aryabhata. So Aryabhata, the roots of the of Aryabhata, he gave us sort of sign tables. He gave us a table of sign values, not in the usual way, but in like second order differences. Interestingly enough, his rule of giving these values, they make use of the so-called discrete version of the the fact that the second derivative of the sign is proportional to the sign. And it's this something actually this what I'm about to mention just now, it ties in very well with your previous point regarding linguistics and language, because in the same verse where Aryabhata gives this description, it is open to two interpretations. One is this the second order derivative of the sign, but also it can also be understood as an application of the so-called fundamental theorem of calculus at the finite discrete case. And so anyway, so from Aryabhata, then people were interested in getting more and more accurate values of the trigonometric functions. So interpolation functions, interpolation methods. Brahmagupta gave his interpolation method for the second order, which today is known as the Newton-Stirling formula. And Vateshwara gave his 96 value angles, table of sign values for 96 angles. And this is how it went on. And finally, the Kerala mathematicians, they for more and more accurate values of the sine and cosine functions, trigonometric functions, they went into really more detail and unlocked the, so to speak, the door to infinity. That's the biggest step. That's the biggest point when it comes to Kerala mathematicians, because how these things like infinitesimals, infinities, and so on. How do you deal with them? And if you look at the works of Madhava, he has many of the important results are given by him, but a lot of important information also is there in his disciples like Neelakantha and Parameshwara, and finally in the works of Jeshtadeva. So he who wrote the Yukti Bhasha. So in the Yukti Bhasha, actually it's like almost like a textbook of calculus, where he gives the the detailed mathematical reasoning behind each and every step involved in the derivation. And in fact, like many students today when they learn calculus, they learn things like how to find out the area of a sphere, volume of a sphere, things like that. So like the reasonings given by Jeshdeva is actually exactly similar to what we learn today in terms of these questions when we learn it from the context of calculus. So this actually and in fact, yeah, and the other great and the other point, very valid important point is the probable transmission of this calculus from India to Kerala. And this is something which is something which also there is a lot of circumstantial evidence that speaks for it, because the Europeans had the motivation, the interest, and the opportunity for getting this knowledge, because they were interested in the reforming the calendar, and like they were interested in navigation, and they knew that the Indians had this knowledge, because obviously Al-Khwarizmi himself had called these numbers as the Indian numbers, so they knew about this. And then yeah, and then there is also this question of how come this knowledge of calculus suddenly springs up in the West all of a sudden without any prior context. So this also, and thirdly, there is also it's a well-known documented fact that Galileo, he had close contact to the Collegio Romano in Italy, and where the Jesuit priests who were sent to India by Christoph Clavius in the 16th century, 16th century, they sent their materials to this University Collegio Romano. And unfortunately there is no record of specific mathematical information having been sent, written record of that. Although, like as C.K. Raju has mentioned in one of his works, he quotes one of the Jesuit priests that he's on the lookout for people who have this knowledge of this. So I think these are some of the aspects that 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 are relevant in the
Absolutely.
context of Kerala mathematics. Yeah.
I think you mentioned about Yukti Bhasha. I just wonder, I mean, can we call algorithms Pramana Yukti maybe, which is basically the idea of having some methods of, getting to Praman, potentially, just a thought there. But in terms of Kerala mathematics, I think there is a lot of these aspects which have been covered in contemporary STEM-related areas as well. I mean, there have been application papers on applications of that, so to say. And I think Gregory and Leibniz series, of course, come a few of the other points that you mentioned. Now, a very pertinent question when it comes to any of the areas that we have covered in Satya Samvad, of course, especially when it relates to elements from the past or conceptual frameworks from the past, is the predictive capacity, right? Is the applicability to the modern context and going forward, right? And within this platform, we try to focus on that as well. So as per your understanding, how do you think we could potentially use Hindu mathematics going forward, not only for decolonization, so to say, but also for, applying it in upcoming areas of interest for us?
I think that so I feel a little bit not well equipped to answer this question. Unfortunately, it sort of falls outside my activity as such. But I would, but when you ask me this question, I am immediately led to think about Manjul Bhargav, the Fields medalist. He has spoken often about how his maybe it was grandfather, or I don't remember who, but who would who was well versed in Sanskrit, and he got a very big exposure to Sanskrit, and the Sanskrit the algorithms of prosody, for example, he speaks about them and how it has been very influential in his work. So this is something that comes to my mind. And another aspect which also comes to my mind is that there was this very interesting quote by Schopenhauer, who is more famous for his philosophy, but he was extremely critical of the geometry of Euclid and the way of thinking that comes with it, the so-called axiomatic mathematics. And he sort of tried to recast this in a form which is very much which is more which is closer in spirit to that of Indian mathematics. So where you have like more intuition based kind of aspects and or algorithmic based aspects. So I have not followed on this in detail, but I plan to do it at some point. And Yeah, and I would just maybe just mention that, actually, that the Indian approach to mathematics, the algorithmic approach to mathematics, definitely, has it reveals facets or aspects of mathematical results which probably would not be there. I mean, when you, for example, consider the fact that, the Greeks or the Europeans for a long time, they did not conceive at all of things like negative numbers, or the concept of zero. So who knows, like, if one immerses oneself more in the spirit of Indian mathematics, it could well be likely that more boundaries are crossed,
Absolutely,
and more
absolutely.
doors are
I
opened.
think
Yeah.
there is a very important area of interest now. I mean, in the current scenario in STEM, especially in category theory, and there are various aspects of category theory, as well as various geometric aspects of that as well, especially in the context of physics, for instance, and in other areas as well. And in Bharatiya Gyan Pranali, we have aspects of category theory in certain strands of thought. So just maybe a possible potential area of work could be in that area as well. I would like to kind of bring this discussion around by asking you, what are your plans going forward, of course, and any parting thoughts for our viewers?
I think one of the most important points that I realized while writing the book, is that one should actually question the official narrative that is surrounding us. And I think that kind of, comes that for that, I think critical thinking becomes really more important, in the sense that one should not accept everything that at face value that one sees, and to, question the basis of the claims that are made. And I would say it is important, not only in the context of Hindu mathematics or Hindu civilization, but actually in like, all walks of life. That is really important. And I think this has been one of the, biggest messages that I have tried to convey to through my book, and which I would also like to convey to the viewers at this point. And yeah, and as such, as regards future plans, I do have some vague plans, but unfortunately not really something very concrete. But hopefully it will materialize as time goes. Hopefully it will come from the realm of the avyakta to the vyakta at some point. Yeah.
Right, right. And we look forward to that transition happening, and hosting you again for the discussion on further points of interest, so to say. And I think I would like to close this discussion with what you just mentioned, which is that, as part of the Infinity Foundation and Satya Samvad, our idea always has been to equip, our viewers, as well as all of us, with, these pertinent points of discussion, these pertinent points of civilizational value as well, which are premised on truth, but which are conveniently hidden at times because of narratives, from the West, from various other, areas of, these agenda-dhari kind of areas of interest, so to say, in the modern parlance. But this has been a fascinating discussion. We really hope to get, your views from all our viewers on this, and take this discussion forward, because there is so much to cover yet in terms of the metaphysics, the philosophy, and now, so to say, the mathematics of the Bharatiya Gyan Pranali. Thank you for joining us today. It was a pleasure having you here with us today, Bhaskarji, and we look forward to having you all, our viewers, in the next episode of Satya Samvad.
Thank you so
Namaskar.
much. Yeah. Namaste.